Last long day that we will have, and today is going to be one heck of a doozy. 2.7, and we'll be doing 2.8 as well. So 2.7, combining functions. Okay, so two functions f and g can be combined to form new functions: f plus g, f minus g, f times g, and f divided by g. So similar to how we can just combine numbers, right? What would be a practice test? Yes, there is a practice test. You will see that on your web assignment. There's a practice test, which is also going to be due the same day that the test will be due. So again, the test will be due Sunday at midnight. And practice test will also expire then. So you have plenty of time to do everything. No excuse to not do it, which again, you guys luck out because I'm also teaching two of these courses. Then they're not they're not synchronous, like they're not meeting. So you guys are essentially getting the online schedule treatment. So that's why you're going to get Monday off. Anyways, going back. Two functions f and g can be combined to form new functions. We talked about that. For example, we define the functions f plus g by, looking here, f plus g. We can say f plus g, again, these are the names of the functions, f plus g of x, all right, the names of the functions combined with the variable that they are defining, right, f plus g of x, and we can change that to f of x plus g of x. Okay, the new function f plus g is called the sum of the functions f and g. Its value at x is f of x plus g of x. Okay, now you can kind of see where this is going. Okay, so adding, subtracting, multiplying, and dividing functions are really just as easy as it looks. So I will go ahead and snip this and put this on our notes. That way you can see it if you do happen to cancel, or not cancel, but if you do happen to download the notes. And then we'll snip the algebra of functions. This is the meat of what we're talking about here. All right, we'll just put this on a new page. Okay, so the algebra of functions, you see that if we take these two functions, of course, this was the example we saw in the paragraph above, right? If we add two functions together, then it just becomes f of x plus g of x. Okay, and same thing with subtraction. We f minus g of x. Well, that's just going to be f of x minus g of x. Same thing with multiplication. Division has one tiny little caveat, right? That being that g of x cannot be equal to 0, obviously, right? So if we have f of x over g of f over g of x, then that just becomes f of x over g of x. Okay. So let's look at an example. Okay, so we're going to combine functions. So let's do this. So f plus g, f minus g. Okay, so this is, we'll just write this out. So a, if we did f plus g, well, this is f, this is g. So we're just going to add those two functions together. We're going to have 1 over x minus 2 plus the square root of x. Okay. And honestly, we're just gonna, I'll snip those solutions because it'll take up a lot of room if I actually do that, right? So f minus g, well, it would just become this minus that. It's honestly as easy as it sounds. Multiplication, we multiply this times this, and of course, let's see, 1 minus x over 2, and we multiply it by the square root of x, okay? Remember that this is essentially saying square root of x over 1, right? And then we just multiply. So it just becomes the square root of x over x minus 2. And of course, it's really messy, but like I said, I'm going to just go and snip the actual solutions, and that way it's a lot more nice and neat. Okay. And then f over g, again, it just becomes a fraction. Okay, this is actually a good fraction to work out, though. So it would be 1 over x minus 2, and it's divided by the square root of x, okay? So if I take this and I divide by the square root of x, so if I take this and I divide it by the square root of x, okay, it looks like this. And if you recall, when you divide by anything, you can multiply by the reciprocal, remember? So if you look at this, you might think of something like this right here, 1 minus x minus 2 over the square root of x. And again, it's not just you that would freak out if you saw something like that. Again, I mean, calculus students, the first or second week, when you see something like that, you're like, oh, man, I forgot what to do here, right? But just remember, we harp back to this, okay? And then we harp back to that, it just becomes, as I said before, you multiply by the reciprocal, which would be 1 over the square root of x, and therefore we would have, 1 over the square root of x times x minus 2. So let's go ahead and snip all those solutions that we just talked about, and then we'll talk about b. Yeah, I feel like this will be a lot nicer and neater. Oh, we didn't even talk about the domains. I'm sorry. Well, we'll let the domains. Okay. Mainly because we need to go back to here. Notice the domains in all of these are A intersect B, okay? And that's also the domain for the division, A intersect B, okay? But also, again, with the division, where we cannot have g of x equal to 0. So if we have the domain being A intersect B, okay, well, what is A and what is B? Okay. What we're doing is we're looking at it reads here, the domain of f here is all values that are not equal to 2. Does that make sense, right? I mean, if we were to take if we were to take the function f, and we would, we say, okay, well, we cannot have a denominator of 0, right? And so what we would do is we would just set the denominator equal to 0. We'd solve for x, and then we would get the value that we cannot have. So yes, we cannot have x is equal to 2. All right, and then g of x, okay, well, what can we not have in a radical, right? We cannot have a negative number. So we would set up the x value to be greater than or equal to 0. Again, I went over all this in our domain Bible that I wrote out in a couple sections ago. So I said domain Bible, I said write this down, I said put a star on it. We're going to be harping back to it quite often, and we will. That's an example of it. Anyways, so the domain of that would be all values greater than or equal to 0. So if I were to find the intersection of x not being equal to 2 and x being greater than or equal to 0, okay, so if we were to take a look at that on the number line, so let's take a look at that on the number line real quick. You can probably visualize this yourself, but number line does help for those of you just, probably might be having morning foggy brain. So infinity here, negative infinity over here. We'll just put the 0 here. 1, 2, 3, 4, 5, 6. Okay, so x cannot be equal to 2. Well, actually, so it can be every single thing but 2. Okay, I always have I have morning foggy brain too. I teach a course also, but before this one at 8 o'clock, and I wake up at 7:30 and I get my cup of coffee. I go over what I'm gonna say and things like that, but I don't actually speak, right? So when I start speaking at 8 o'clock, things just do not come out right. My voice sounds froggy. Everything's awful for the first 15 minutes. But anyways, and then g, x being greater than or equal to 0. Okay, so it means we have as a closed circle here at 0, and we're going all the way to infinity. Okay, so where do these two domains intersect? Okay, well, they intersect from 0 to infinity, it looks like, right? Except for at 2, right? The green and blue line overlap each other everywhere except for at 2, because the blue does not actually touch 2. And so we would write this like this, from 0 to 2, and then again, the parentheses means we're actually not touching 2, right? union with 2 to infinity. So when we talk about the intersection of the domains of A and B, that's what we're talking about, the intersections of these two domains. Okay. So that was, sorry I skipped over that one really fast. I know we have a lot on our plate and I'm trying to scoot through it. And again, as we saw on the previous page, the domain of addition, subtraction, and multiplication, they're all the same. Okay, only the division is different, and that's just to make sure that the denominator is not equal to 0. Okay, and because we're using the exact same domains essentially, right? We have to also contend with the fact that the denominator here, okay, we can't just say greater than or equal to 0, can we? No, because if we were to make the denominator 0 here, right? Well, then we would get 1 over 0, which is 0. So instead of writing our domains just like we did with the addition, subtraction, and multiplication, we can't say greater than or equal to 0. See? Instead we have to say just simply greater than 0. Because if we were to equal it to 0, then we would get a 0 in the denominator here. And again, it's not too much to think about. I feel like domains. Well, actually, I'm going to take it back. I think domains don't actually come as naturally because we're so used to solving for x, and then so when we get to domains, we're not necessarily solving for x. We're trying to figure out what we can use. So if that's confusing you, obviously contact me. Okay. And then lastly, I'm just going to snip this as well. We're just evaluating functions at a point. This is the B. So we have the f plus 4 already given. We already did f plus 4, right? Which was 1 over x minus 2 plus square root of x. All we're going to do here is plug in 4 everywhere where there's an x and solve. Okay, so that's how we evaluate each function at those points. Let's moving on. Okay, that's graphing it. We're going to skip the graphing part. Okay, now we get to something that I know none of you like. Composite functions. We'll just jump straight to the definition. Okay, so composite functions. Again, this is another one of those things where when I was taking this course as an undergrad, I wasn't majoring in mathematics. I had no intention of going into mathematics. I was again behavioral science. So when I got to compositions of functions, I just thought, huh. All right, so this isn't normal. This isn't stuff that I'm used to. I hope there's not a lot of these on the test because I'm not even going to try. But again, I was a very lazy student. Don't be me. Given two functions, f and g, the composite function, and then this is an f, and then it's an open circle there, of, f, and then of g, okay? F of g, also called the composition of f and g, is defined by, okay, so if we have f of g, if we have this notation right here, okay, what this is saying is we're going to be putting g of x into f of x. Or we're taking the function f of g of x. So in the past, let's do this. Let's have some f of x, and we're gonna call it x plus 7. Okay, we're gonna have some g of x. We're gonna make it blue. We're gonna call it square root of pi. Okay, so if we take f of g of x, right? In the past, we might have done something like this. We might have done, all right, so evaluate the function, f of 3. Okay. Well, if we evaluate the function f of 3, then we put 3 everywhere where there's an x. Okay, and that's essentially what we did on the B part of example 1, right? When we took f plus g of 4, we put a 4 everywhere where you see an x. Okay. So that's essentially what we're doing there, right? But if we're taking a composite function, So now let's take f of, and let's actually do the notation here, f of g of x, okay? Well, in the definition above, right here, it tells me that that is the same thing as saying f of g of x, okay? So what I would do is I would replace the g of x here with the g of x here, which is square root of pi. I'm sorry, square root of pi. Square root of pi. Okay, so then I would put square root of pi everywhere where I see an x. Okay, so similar to how we did, f of 3, f of 7, where we evaluated a function at a value, we are evaluating a function now at a function. Okay, so this is composite functions. And of course, we'll get nice, good examples here in a moment. Better examples than I come up with there. I'm not sure the diagram is that great. Oh, the domain. Now this is huge. Okay, so this is the domain I want to talk about. We'll just take the picture, whatever. Okay, we'll take the picture with us. I don't think it's particularly useful, but it is referenced in the domain part. Okay, so real quickly, this reads, the domain of f of g is a set of all x in the domain of g such that g of x is the domain of f. That means nothing to you, right? So let me break that down for you. So let's move these off to the side here, so I can give you my better definition of finding the domain. So let's do this. The domain, this is something you want to write down. Domain of, that doesn't look like a good D, does it? Whatever. The domain of f of g of x, okay, will be the domain of f of x. So I'm going to put f and put a little d there. So meaning the domain of f. No, sorry, let's do it this way. Not just the domain of f. It's going to be the domain of f of g of x. Okay, little d down there, and we're going to be intersected with the domain of g of x. We'll put g of x there. Okay, so this is this written in better words, better notation. So basically what we're doing is we're going to find the domain of our composite function, okay? And then we're going to find the domain of our whatever function we're essentially compositing in there, right? Whatever function we're actually inserting. And this particular, my definition here, I'm inserting g into f. So it's going to be the intersection of what you insert intersected with the domain of your actual composite. And that is confusing, so let's do an example. Not current, sorry. Okay, so we're going to let f of x equals to x squared and g of x equals to x minus 3. So let's find, first off, we're going to find f of g. So we'll find f of g of x. We'll put of x here. Okay, so f of g of x, I'm putting g of x everywhere where I see an x and f of x. Again, it's the same thing as saying, when we evaluated at a value, right? Evaluated, f of x at 7, we plug in 7 everywhere where we see x. In this particular case, we're plugging in a function. We're not plugging in a number now. We're going to put in a whole function. Okay, so this would become, so x squared is f, so I'm going to put in x minus 3 for x, and then it's squared, right? My normal x was just simply x squared. I replaced that x with the function g, which was x minus 3. So that's f of g. So we need to find the domain now, and this is really easy actually, because, well, the first thing we're going to do is, I said we're going to find the domain of f of g, f of g of x, okay, intersected with the domain of g of x. I think I'm putting a little subscript d there, denoting domain. Okay, well, let's look at the domain of my composite function. Well, we hark back to our domain Bible. I said that every function, the domain is negative infinity to positive infinity unless the two criteria are right, and neither of those criteria are fulfilled here, right? We don't have a variable in the denominator, nor do we have a variable in an even root, right? So the domain of f of g of x is all real numbers, okay? And then if I look at the domain of g of x, same thing, right? It's a linear equation. There's not a variable in the denominator. There's not a variable in a radical. So it's going to be, real numbers intersected with real numbers, and therefore the domain is just going to be all real numbers. Okay. So the domain here is all real numbers. You can also write it like this: negative infinity to positive infinity. Okay, same thing. Next up, we're going to do g of f of x. Okay, so just a little bit of reverse here. So now we're going to be plugging in x squared everywhere where I see an x and g. Okay, so I'm going to put x squared basically for x. So this becomes just simply x squared minus 3. Okay, well, what's the domain of this? Well, it's all real numbers, right? Again, another not linear equation, another equation that does not have a variable in the denominator, nor does it have a variable in an even root, right? And then, of course, the domain of g of x is a change, so it becomes, the same thing. The domain is all real numbers, all real numbers, or again, you can just write that as negative infinity to positive infinity. All right, so B, we're going to find f of g of 5. Okay, well, this is f of g. We plug in 5 here. So 5 minus 2 is 2. 2 squared is 4. So this would be 4. And g of f of 7, we plug in 7 here. So 49 minus 3 is 46. And that is g of f of 7. Where do you see? That's a minus 3. Yes, sir. Well, yeah, well, because 2 squared is 4. You're good. So yeah, and then 49 minus 30, 40. Okay, just making sure. Look, I understand. It happens to me all the time. Okay, no problem. So let's move on. Yeah, 4 and 46. We're good. We're good. Everything's good. This is definitely one I'm going to be snipping, because that is a lot of stuff that I don't feel like writing today. Because again, we have a whole other section to get to. But this is just another example. Obviously, I'll talk about it, but we're just going to snip this instead of writing it all out. Holy smokes, that's a lot of stuff. Well, that's just gonna have to do. Okay, so I need a graph attached to this. And they're fine. Okay, so if we want to find the composite functions, all right, so we are inserting in these like crazy. We're also putting f in f, we're putting g in g, so on and so forth, right? So something I want to talk about real quick, let's talk about a, because I feel like some of you might have forgotten something along the lines of, okay, so if I take the square root of a square root, how in the world do I get the fourth root, if you can see that? Okay, well, real quick, the reason why is because, think about this, the square root of x, if you recall, is the same thing as saying x to the 1/2, right? So if I were to look at a, that's saying the the square root of 2 minus x raised to the 1/2 power. Okay, so that's this square root inside the square root. Or in other words, if I took off the radical here, then that would be all of this raised to the 1/2. And if you take an exponent raised to an exponent, if you recall, you multiply. Okay, you multiply the exponent, so it becomes 1/4, and that's how we get the fourth root. Okay, if you struggle with that, it's in the review sections. Go back and do that, and obviously email me. That's probably always the quickest, isn't it? And then of course the domains, as we talked about, would be the intersection of those. Let's see if there's any other computation here that I need to probably discuss. Same concept here. The square root of a square root is simply the fourth root, because you raise that power to a power. And nothing more in D as well, just kind of tedious stuff. Other than that, again, I do feel like I'm cheating a little bit here, but today's a long day. The next section is even longer. Okay, so a composite of three functions. The way this works is you just kind of go backwards, right? You're going to put h into g, and then you're going to put g of h into f. Okay, so notice how here we put h into g. So h of x was x plus 3. We're going to plug it into g of x, so it's going to be x plus 3 raised to the 10th power, and that's what you see here. And then you're going to plug that into f, which is x divided by x plus 1. So you're going to be putting x plus 3 raised to the 10th power everywhere where you see an x. We have an x in the numerator, an x in the denominator, and that's where we see these. Okay, so I'll just go ahead and write it like this maybe. F of g of h. I don't know if this will help out too much, but that's how we do it. We plug h into g, and then we put g of h into f, and that's how we proceed. Okay, so recognizing a composite function. You've seen composite functions already before in many ways. It's just now we are naming it. We name it a composite function now. So given, all right, this is just a big F, big F, big function, is the fourth root of x plus 9. Find the functions f and g such that the big function is g of x plugged into f of x. Okay, so what we'll do is we'll look at this function here. We know that it looks like it's broken down into the fourth root of some x and x plus 9. Okay, it's broken down into these two functions, right? And then all this becomes is, if this was f, let's write it a little bit smaller and neater. So 4th root of x, and what I say, x plus 9. Okay, that's what we said we can break it down into. So if we called the 4th root of x f of x, and if we called x plus 9 g of x, then we do indeed see that if we were to plug in, if we were to have f of g of x, we'd plug this into our x here, which would get our big F that we saw, which would be the 4th root of x plus 9, which again was equal to big F of x. Okay. Okay, I believe that does it for this section. Now, believe it or not, the long section. Okay, so 1-1 functions and their inverses. So the inverse function, I'm going to go and snip this too, probably. The inverse of a function is a rule that acts on the output of the function and produces the corresponding input. So basically what we're doing is, you think about inverse, right? Inverse is, you just kind of reverse it, right? So normally if you're going left to right, if you invert it, you go right to left, right? So that's essentially the thought process here. So the inverse undoes or reverses what the function has done. So if we have some function, f, we're just going to call it f, okay? And we take that function and we go from, point A and we go to point B. Okay? The inverse function will go from B back to A. Also, and I'm pretty sure this is going to pop up here in a moment when I look at the definition, but we're used to if I had x to the -1 power, okay? If you recall, x to the -1 power is 1 over x, right? That's true. Okay, that's if the -1 is an exponent. This -1 is not an exponent. It is notation, okay? And similar to how you have a, the difference between a domain and a point. So what I mean by that is, if I said just simply 3, 7, if I said 3, 7 with no context, you would think that's a point on a graph, right? But with context, that could also be the domain from 3 to 7, not including 3 and not including 7. Okay, same thing here. You will have the context knowing that this is the inverse function as opposed to, 1 over f, which is not right. And again, it's probably more eloquently put here in a moment. But other than that, let's move on. So let's compare the functions f and g whose arrow diagrams are shown in figure 1. Note that f never takes on the same value twice. So if we were to look at this function here, going from set A to set B, notice how every one of them goes to only one one element in set B. Whereas this one, this is not 1 to 1. We have 1x, but here we're going to 3 and 2. They're going to a singular set in B, notably 4, right? So this is not 1 to 1. You can think of 1 to 1, just honestly, it's about as simple as it sounds, right? 1 to 1, right? You can only have 1x go to 1y. So real quick, let's do this, because I think this is kind of confusing for some people here. So we have equations. Let's write that better. See, I'm a heavy writer, right? And I'm left-handed, so I like to put my palm, not palm, my palm, but my hand on like the paper and stuff. But since I'm writing on a tablet, I can't put my wrist down, and I can't make it look nice and neat. But anyways, we have our equation, okay, and a subset of the equation is the function. That's awful too. Golly. F U N C. Okay. This is embarrassing. Whatever, guys. That says function, okay? We have a function, okay? And we know functions are one element in x goes to only 1 in y, but you can have multiple x's go to multiple y's, such as x squared, right? 2 goes to 4, so does negative 2. Negative 2 also goes to 4. But what makes a function is that value 2 will only go to 1y. Okay, so let's see here. An example of just simply an equation would be, circle equations, right? Circle equations look like this, right? And, oh, that's not what I wanted. Like this, and we can have multiple x values go to multiple y values. That's an equation, right? Something like that. And then a subset of the equation, as I said, is a function where we have only one y being the output for one x. And then below this function is a one-to-one function. 1 to 1. Okay, so think of one-to-one functions more of as like a subset of a function. A special case, rather, okay? So if we were to look at, now let's look at the definition, I guess. Did we even finish this up here? Yeah, pretty much. Okay, so definition of a one-to-one function. A function with domain A is called a one-to-one function if no two elements of A have the same image. That is, if I take f of x1 and it is not equal to f of x2. So let's think about that. And again, I said x squared is a function, right? It is a function. It passes that vertical line test, but it is not one-to-one, because if I were to graph this, okay, let's make it more precise, I guess. If I were to graph, that's not as precise. All right, well, that's just gonna have to do. This is saying f of x1 is not equal to f of x2. Well, the example I used was 2, right? If I had 2 here, negative 2 here. Well, again, what is 2 squared? Well, that's 4. What is, that is an awful drawing. But we know negative 2 squared is also 4. So that would make it not a one-to-one function. And this is how we test graphically for a one-to-one function. So we know that if we want to test to see if an equation is a function, we have our vertical line test, right? Now if we want to test that if our function is a one-to-one function, we have a horizontal line test. And it behaves the same way you would do your vertical line test, right? If you intersect your graph in more than one spot, then it is not one-to-one. Okay, so x cubed, and this is where knowing what your parent functions look like. Another example of why you need to memorize that. All right, again, that's from Chapter 2, Section 1, the parent functions that we talked about. You have got to memorize them. That way you can immediately recall what they look like and how they behave. Okay, so example 1, is the function x cubed 1 to 1? Well, looking at the function x cubed, it is indeed 1 to 1 because, number 1, it passes that horizontal line test, right? Is there a number 2? Maybe there's not a number 2. Well, anyways, it is indeed a 1 to 1 function because it passes that horizontal line test. X squared. Again, we know what x squared is, right? That's probably the one that we're definitely going to not forget about, is it? Right. And again, we know it's a parabola. It indeed does not pass that vertical line test. Oh, this is actually pretty good. Another reason why restricting domains is an important exercise. Yeah. Okay, so this reads, although the function g is not 1 to 1, it is possible to restrict the domain so the resulting function is 1 to 1. So if we wrote g of x up here like this, g of x is equal to x squared, but then we restricted the domain to only values that are greater than or equal to 0, then we do indeed have a 1 to 1 function. Okay, so we can manipulate graphs kind of by restricting domains, and we'll see a lot of that later on. Not today, though, I don't think. Okay. And example 3, we know 3x plus 4 is a linear equation. Do we have the graph of it? No. Okay. Well, regardless, we know that 3x plus 4 is just a linear equation with y-intercept at 4 and a slope of 3. And it's a positive slope, so it's just going to look like this. And we know that that graph is indeed going to be 1 to 1, right? It passes the horizontal line test everywhere, and it is a 1 to 1 function. So knowing when you see a a cubic a cubic equation, quadratic equation, linear equations, things like that, the parent functions we talked about in section 1, knowing their behavior, you can easily say, real quickly, if it is indeed a 1-1 function or if it is not. Next up, the inverse function. Okay, so this is fun. All right, actually, I can't just go ahead and put it on this page here. But we're just going to recall, okay? So I said we have equations. I said we have equations. And beneath equations, I have functions. Functions, whatever. And then beneath functions, I have 1-to-1 functions. Okay. And then beneath 1-to-1 functions, I'm going to have inverse functions. Inverse. We're just going to put inv. Okay. So real quick, before we proceed with that process, let's look at the definition. Definition of inverse function. So let f be 1-to-1 function. So that alone tells me that in order to have an inverse function, we must be a one-to-one function. In order for it to be a one-to-one function, it must be a function. And of course, in order to be a function, it must be an equation, right? Whatever. So that's the tree that we're looking at here. Let be a one-to-one function with domain A and range B. Then its inverse function, f inverse, has domain B and range A, and is defined by f inverse of y is equal to x, and that is equal to f of x equal to y. Okay, so real quick, let's look at this. No, let's look at this. Okay, this is going to come back probably in this section as well. So let's look at that. Should we go on a different page? No, we'll put it here. Okay, so if we have f here, and if we have f inverse here. Okay, so I'm going to put a D and an R standing for domain and range. Oops, domain and range. Okay, so if the domain of f, okay, we're just gonna call it alpha, and the range of f we're gonna just call it beta. Okay, well then the domain of the inverse function will be beta, and the range will be alpha. By the way, this is super duper important. It needs to be written down. Okay, if we have, again, just some alpha, some beta, it doesn't matter. Okay, then all you do for the inverse function is change the alphas and betas. That's it. And of course, I use alpha and beta instead of something like 3 to 9, and then whatever. But I'm pretty sure we might see an example of it today. If not, we'll definitely will later on, especially when we get into logarithms and such. In the meantime, looking at things algebraically like this, this is mind-bogglingly simple. So simple that I enjoy teaching it. Okay, so starting here, we have if. Okay, we don't know what the function looks like. We just know that if we evaluate a function at some value, then it's equal to something, right? So if f of 1 is equal to 5, if f of 3 is equal to 7, and if f of a is equal to negative 10, then we want to find f inverse of 5, f inverse of 7, f inverse of negative 10. Okay, well, all we got to do is map back to where we found the 5, where we found the 7, where we found the 10, right? So where did we find the 5? Well, we found it at f of 1. So f inverse of 5 is equal to 1. Again, f inverse of 7, right? Well, how did we originally map to 7? Well, we took f of 3 to get to 7. Okay, so therefore f inverse of 7 is going to be 3. Same procedure for f inverse of negative 10. How do we get to negative 10? Well, we evaluated f at 8. So therefore f inverse of negative 10 will be f of 8, or will be 8, because f of 8 is equal to negative 10. Yeah, that's a lot of drawing on this, but that's it. All right, so this is what I was saying earlier about mistaking that negative 1 for an exponent, essentially flipping it around. F inverse of x is not 1 over f of x like we would do with an exponent. Okay, so don't do that. I might have said that a lot more eloquently than that, huh? Okay, finding inverse functions. Is that it? Okay, excuse me. So anyways, looking or finding values of inverse functions graphically. So we did the last example was kind of algebraically, mainly I guess to get your feet wet. But if we want to find values of inverse functions graphically, we can find specific values of inverse functions from the table or graph of a function itself. So the table below gives values of function h. So this is the table, gives values of function h. From the table, we see that h inverse of 8 is equal to 3. Okay, so let's think about that real quick. Finding values of h inverse from a table of h. So h inverse of 8 is equal to 3. We see that 8 does indeed map to 3, and then we can see that for the other examples as well. H inverse of 12 is equal to 4, and then I'm sure the last one would be 3 to 6. Okay, so again, similar to the last problem, you just kind of work things backwards, right? Similar to, I don't know, I guess similar to the word just itself, right? Inverse. You just move things backwards. And of course, a graph of function f is shown. All right, so first of all, we're going to look at this graph, and since this is a one-to-one, since we are talking about inverse functions, then in order to qualify for an inverse function, the function must be a one-to-one function, and we do indeed see that this graph is one-to-one. Okay, that's not part of the problem, but just wanted to express that. And we see that f inverse of 5 is equal to 7. So let's look at this. If we were to call just this normal function f of x, looking here, what is f of 4? Well, f of 4, I go to the x-axis, and I go up to the graph, and I see where we're intersecting. And we're intersecting at 3. Okay? And if I were to, again, this is just pretend that we don't know anything about inverse function. We're just going back to our normal function ideas here. Okay, so if we did f of 7, well, f of 7, where is that graph? Well, it intersects at 5. So we have f of 4 is equal to 3, and f of 7 is equal to 5. Sorry, I couldn't see it. Okay, well, if I were to do things backwards, right? If I were to say f inverse of x, then I would see that the 3 maps to 4. Is that the same thing? Same graph? I don't think so. Anyways, we see that if we map things backwards, we would say f inverse of x, we would say f inverse of 3, well, that maps to 4. F inverse of 5, well, that maps to 7. Again, it's basically going from looking at the x-axis to see where we intercept on the y, to looking at the y-axis and seeing where we intercept on the x. Oops, sir. Okay, so we can find the inverse of a function. Let's see. Actually, okay, so we can tell if a function is an inverse function graphically, right? A 1-1 function rather. A 1-1 function again is an inverse function. I'm sorry, an inverse function is a 1-to-1 function. I have that backwards. We can tell graphically by using the horizontal line test, right? So if I take an equation and I graph it, I can tell if it's 1-to-1. Well, what if I don't have a calculator on me? All right, that and to be able to do things computationally, how do I figure that out algebraically? Well, to figure things out algebraically, we follow this, the inverse function property. So reading this, it says, let f be a 1-1 function with domain A and range B. The inverse function, f inverse, satisfies the following cancellation properties. So this is saying, right here, if I take f inverse of f of x, if I take the inverse function and I composite it with f of x, then I should get x. And if I take the normal function, the f, and I composite it with the inverse function, then I should also get x. Okay, and if I get x there in both cases, then I know that both that function f inverse of x and f of x are inverses of one another. Okay, so where does this come into play? here. Okay, so this reads, show that f of x and g of x are inverses of one another. Okay, so obviously we're running under the assumption that they are indeed inverses of one another, but look, you know, I'm certain I put some homework problems in that ask you if they're inverse functions. So what we do is we're going to take f of g of x. Okay, so we're going to plug in g of x everywhere where you see an x and f of x. So again, our composite function. So we have x to the 1/3. We plug that in for this x here, which is up to raise to the third power. If we raise an exponent to an exponent, we get x to the 3/3, or in other words, x. Okay, so that's f of g of x. Well, what is g of f of x? Okay, so same thing. Now we're going to be putting f of x in for g of x. So we're going to put the x cubed in for this x right here. So it's x to the 1/3. So x cubed. I forgot to put my cube there. Let's rewrite that. X cubed raised to the 1/3, and of course that's, you know, same thing there. So that's equal to x. So since f of g of x and g of f of x, let's change colors. Again, let's restart. Since f of g of x and g of f of x, since they both gave me an x as a solution, then these two functions, f and g, they are indeed inverse functions of one another. Okay. So this is how we find inverse functions algebraically. And I got a little ahead of myself. We're going to figure out how to find inverse functions graphically towards the end of this section. Just remembered. Okay, so finding the inverse of functions. So here's what we're going to do. We're going to I don't follow that 3-step process. I do it a different way. Shocker, I know. Yeah. So if you want to go by the book, you're more than welcome to. But I'm going to do it the way I've always done it. And again, it's doing things different from this book isn't very radical. This book sucks. I hate this book. Anyways. So if I want to find the inverse function, here's what we're going to do. All right, we're going to say step 1. Okay, we're going to change. Oh, there's a lot of writing here. Change f of x to y. So this looks like this. We're going to say y is equal to 3x minus 2. Step 2, we're going to interchange x and y. So it's going to look like this now. It's going to be x is equal to 3y minus 2. And we're going to go to step 3, which will be on the next page. 3. We're going to solve for y. So what was that? It was x equals 3y minus 2. So x equals 3y minus 2. Can I do that real quick? X equals 3y minus 2. Let's just write it out. Okay, so we went from x equals 3y minus 2. If I were to solve this for y, like I wrote, we're going to add 2 and divide by 3. So it's going to be x plus 2 divided by 3. So y is equal to x plus 2 divided by 3. And then step 4, we're going to replace. Does that even look like replace? It does. It does to me, whatever. Y with f inverse of x. So we're going to say f inverse of x is equal to x plus 2 divided by 3. Whew, okay, so let's recap real quick because I feel like I did a lot of that under my breath. So step one, in order to find the inverse function, is we're going to change f of x to y. So in this equation, we changed this f of x into a y. Boom. Okay. Number two, we're going to interchange x and y. So what we did was we took the x, replaced it with y. We took the y, replaced it with x. Boom. Step three, we solved for y. Nothing hard, right? We just added 2 to both sides and then divide by 3. Boom. And then lastly, we replaced y with f inverse of x. And so we replace this y with f inverse of x, and we're done. Oh, that's not what I wanted. Oh, no, I can't undo. Well, that's just going to stay there. Okay, so that's it. That's the steps to find the inverse function. Do we have to do anything else? No, that's it. We just had to find the inverse function. So again, I mean, this is, let's see, what do I do different from this? We do the number one. All right, so number two, I change x and y. I don't solve the equation for x in terms of y. They interchange it. Whatever, I don't care. Do it the way I told you to. You'll be better for it. Okay, so find the inverse function here. So once again, we're going to step one. I'm not going to actually write it out anymore. So okay, so I'm not going to write in words rather. So step one, we change f of x to y. So we got y is equal to x to the 5th minus 3 over 2. Step two, I interchanged x and y. So I've got x is equal to y to the 5th minus 3 over 2. Step three, probably have to do it 1/2 5th root. No, I don't have to do anything too dramatic here. So step three. All right, so I'm just gonna do this in my head, right? I'm gonna multiply by 2, so I'll have 2x. Okay, so and then I'm gonna add 3 to it, so it'll be 2x plus 3, and then I'm gonna take the 5th root of both sides. So this becomes y is equal to the 5th root of 2x plus 3. Okay, hopefully you followed along there. All I did was take this and solve for y. Okay, and then step 4, I said I changed y to f inverse of x. So I've got the 5th root of 2x plus 3. Okay, and that's it. We found the inverse. That's pretty easy, huh? Just follow those 4 steps. I know there's the harder one somewhere though. And of course, you can always check your answer by doing what we did in that one example. Oh, this is what I'm thinking of. Okay, so this is usually, I think, my exit problem. Let's see. Okay, I think so. I just go back to it, I think. Okay. So let's do this. This again, like I said, this is usually my exit problem. So when I'm in the classroom, I like to keep students as long as possible because I don't like being the good guy in their life. I like being the bad guy, and so I make them usually solve a problem before they can leave. And this one's a really good one. But unfortunately, we're online, so I can't keep you as long as I possibly can. So step one, we're trying to find the inverse function. We're going to change the f of x to a y. So 2x plus 3, x minus 1. All right, step two, we interchanged, right? So we've got the x here is equal to 2y plus 3, y minus 1. Step three, now this is where we're tricky, okay? Step three, let's put step three up here because it's going to take a minute. Not really, but just a thought process. So we have a y both in the numerator and both in the denominator. Okay, so first of all, let's get rid of the fraction. So what we would do, obviously, is we would multiply both sides by y minus 1. So I'll have an x times y minus 1, and then the right side becomes 2y plus 3. Now we're trying to solve for y, right? And now, but I have a y on the left side and a y on the right side. This is where, excuse me, this is where just the simple computation that you thought was mundane comes into play, and you might have forgotten about it because like I said, it's my exit problem, and I get plenty of students that are like, I don't know what to do. So at this point, I'm like, okay, we got y's on both sides. I need to get a y on either side, right? Obviously, you're not going to divide by this because you would get right back to this, right? So we're not going to do that. Instead, what we're going to do is we're going to break down that parentheses there. So we're going to say x, y minus x is equal to 2y plus 3. That doesn't really get us too far because, I mean, we still have the y on the left side and the right side. Okay, but let's move forward with still the end goal of getting the y by itself. So what I'm going to do is simultaneously add x to both sides and subtract 2y from both sides. So I'll have xy minus 2y is equal to x plus 3. Okay, so hopefully it's coming more under focus now, right? So now I'm going to factor out a y on the left side. And that leaves me with x minus 2 is equal to x plus 3. And then now we see what we're looking for, right? We divide both sides by x minus 2, so we've got y is equal to x plus 3 over x minus 2. And then, like I said before, we'll just go ahead and make this step 4 here and change this y to a f inverse of x. Okay, so that one I wouldn't say is tricky, but it is definitely, again, one of those things where all the things that you learned in, maybe algebra essentials, college algebra, or all the math that you took in high school, where you thought that was mundane, and you're like, well, I'm never going to use this. Well, we're using it. There it is. Boom, you're welcome. Okay. So earlier, again, I kind of got ahead of myself, and I talked about confirming that functions are inverses to one another algebraically. And of course, again, and that was because, or not because, that was by this, example 6, right? You took the composite function, f of g of x and g of f of x. If your solutions are both x, then they are indeed inverse functions of one another. Well, in order to figure that out graphically, like with anything graphically, it's going to be easier. We'll just, I don't think figure 9 gives much there. Okay, so there. Okay, good. Okay, so this is how we do it graphically. Right? Again, algebraically, you take the composite functions, and if you get x for both, then you're good to go. This line here is the line y is equal to x. Okay, it's the identity function. Two functions are inverse functions of one another if they are reflective about that line y is equal to x. So if we have this blue line, it looks like this. Okay. Well, the inverse function of that will be mirrored across that line y is equal to x. It will look like this red line. That is how you tell if functions are inverses of one another graphically. Again, we've already done it algebraically. This is now graphically. Did I snip? Okay, good. I did that. And so sketch the graph of f of x equal to the square root of x minus 2. Now here's the thing. We know what it looks like, don't we? We have an idea of what it looks like because we did this the other day by graphing things in our head, right? I don't want to white. Okay, so f of x we know is the absolute value function, which looks like this, okay? But we are subtracting 2 from the variable, right? So since we're subtracting 2 from the variable, that means we're going to move this graph to the right 2 units, like this, okay? Well, let's go back and think about the identity function. It looks something like this, okay? And if I were to sketch that graph, now B says use the graph of f to sketch the graph of f inverse. Well, then it would look something like this. That's it. Pretty easy, right? And then lastly, it says to find an equation for f inverse. So let's just go ahead and do that. You know, honestly, I was gonna snip the actual graph, the actual figure in the book, but I think that's a pretty good picture. One of my best ones. So find an equation for f inverse. So we're gonna step 1. Y is equal to the square root of x minus 2. Step 2, we interchange. X is equal to the square root of y minus 2. Step 3, we solve for y. So what we're doing here, we're going to square both sides and add 2. So this becomes y is equal to x squared plus 2. Okay, and then step 4, we've got f, that's horrible, f inverse x is equal to x squared plus 2. And that's it. So we sketch the graph, and let's put it over here. Let's say we're going to denote the blue as f of x. Ooh, that's not x. F of x. And the red is f inverse of x. We did that. We used the graph of s. Well, we did that. And C, we found an equation for f inverse. Right? And I believe that is it for the section. So that concludes